Let's take a look at some probability properties. Now, these properties are something you guys are already aware of. You even learned this back at SHS, that is from your set theory, those time. Yeah. So with this set theories, we are going to look at popular terms that we are already aware of. Now we can think of what complement of an event. You can think of union between two events, their intersection, as well as what also another thing called the mutually exclusive events. We are going to look at all this. Now, once we talk about complement of an event, suppose that we should have an event that is defined to be an event consisting of some sample points. So suppose that we have a set of, let's say, points. Let's call it what? A. Let's call it an event A. Now, this complement, or should we say complement of A, refers to all the sets that, or the sample points that are not in what? The event what? A. So suppose that we have event, let's say for 1, 2, 3, up to, let's say the next one happens to be 5, and let's say 9. And suppose that we are looking for a complement. Once we are talking about complement, we could either denote it by a prime or just a complement as we have in here. No, once we talk about complement, this complement refers to all the elements that are not found in what? This set. So we could have it as a Venn diagram as we have in here. So the whole of this happens to be a sample space, and suppose that we have this bounded region to be our event. This A complement is all about elements that are not found within this what? Event. So anything beyond this space, anything being found in this blue colored what region is our A what? Complement. So that is also that. Now let's talk about the unions of two events. Now suppose that we have event A and event B, and we like to look at their union. It's more or less like the addition of these two events. Now, this union could also be represented as using the word or. So anytime we should have this statement, A or B, this is also the same as what? A union what? B. So anytime we have union or A or B, it's just the same as adding the two events that we are what? Dealing with. You could also look at their intersections, okay, whereby this intersection refers to the elements that two set of events have in common. So suppose that we have event A and event B, and we would like to look at their intersection. This intersection refers to the point or the outcome that these two events have in common. So this is what is being represented by this region that we have here. So in place of using the intersection symbol, we could use the word and. So if we should have A and B, that is the same as what? A intersection B. And that refers to what? The things these two have in common. That is that. Now we could also think about mutually exclusive events. Now with mutually exclusive events, we say that two events are said to be mutually exclusive if these two events have nothing in common. In other words, that is to say that they have no sample point what in common. So looking at this Venn diagram, you could see that you have event A and event B, but they don't have what? Anything in common. So with these two events, they cannot occur at the same time because they have what? Nothing in common. So anytime you hear the word mutually exclusive, it means that this event or the event under study have nothing in common, and hence they cannot occur at the same one time, or they don't have anything in common. So let's take a look at some examples. So suppose that with a gas station, that problem, suppose that we have an event where event A where we had 0, 1, 2, 4, and 3. That is an experiment in which the number of pumps in use at a single 6-pump gas station is observed. So in this case, we are using only one of the gas stations for now. And remember, each pump or each station has 6 pumps. So suppose that we have an event A where we have 0, 1, 2, 3, and 4. All of these pumps were being used, okay? And also an event B where we had 3 pumps, 4 pumps, 5 pumps, and as well as 6 pumps being used. And finally, an event C where we only have 1, 3, and 5 pumps being used at a certain time. So with this, let's see how we get to generate or come up with these properties that we just talked about. So once we talk about A complement, remember that this refers to elements that are not found in the original element, and because this is A complement, meaning the elements that are not found in element, or let's say set A or event A. Now remember that we did have what, 6 pumps, and looking at this, the elements that we cannot find in this are 5 and 6. So meaning that if we are looking for A complement, we are going to just have 5 and 6, because 5 and 6 cannot be found in what, event what, A. Now let's look at A union B, or A or B. Remember that this union symbol is the same as or. Yeah. So remember that with this union, all that we are trying to do is just try to combine these two events. Now in combining these two events, that is A and B, we have 0 in here, we have 2 in here, we have 3 in here. That is combining. Because we have 3 and 3 here, we are just going to write only one of it. Now we have 4, we have 5, we have 6, okay? That is combining these two events together. And remember that the whole sample space was from 0 to 1, and this is the same as the entire sample space. So that is why we also have this here, denoting that it's the same as the sample space. Now let's look at A union C. That is the combination of event A, and event C. So we do have 0, we do have 1, we do have 2, we do have 3, we do have 4, we do have 5, but we do not have 6. So A union B is going to start from 0 up to 5. Now let's look at A intersection B. Now with A intersection B, remember we are looking for things that they do have in common. So looking at A intersection B, A and B, what do they have in common? Yeah, you can think about 3. We have 3 here. We also have 3 here. We also have 4 here. We also have 4 here. But the remaining cannot be found in both. So that is why we have 3 and 4 here. So the intersection referring to what they do have in common. Now let's look at A intersection B. Now A intersection B, we are having 3 is here. We have 3 is here. So with this, also we also have 1 here and 1 here. So once we are dealing with A intersection B, we have only 1 and 3. And that is what we have here. Now let's look at an interesting one where we are combining more of these, okay? So with this, we have, suppose we are looking for A intersection B complement. Now remember that A intersection B has been estimated to be 1 and 3. Now this complement now brings us back to which element can be found in the sample space but not in this A intersection B. Now looking at the sample space where we had 0 to 6, you could see that 0 is not here, 2 is not here, 4 is not here, 5 is not here, 6 is not here. So A intersection C complement is what we have here. So these are elements that cannot be found in this A intersection C, but can be found in the sample space. So that is also that. Now let's look at another example, okay? And in this case, we are looking at the C++ program. Now with this C++ compilation experiment, suppose that event A, B, and C are defined as follows. So A is equal to a situation where the student was able to successfully run at the first time. He failed for the first, but able to run at that and up to this point. So this up to makes the first event, and the second event, and the third event, that is the C. Suppose that we are looking for what? A complement. A complement will be all the sets that was not what found in A. And remember, once it comes to C++ compilation, you could have so many what infinite number of what outcomes. Because it could be that someone will run for like even more than 50 times before he gets the whole code what right. So we have so many. The same thing applies to what? The C complement. Now with the C complement, we don't have S in here. That is achieving a success for the first time. We don't have it here. Also, we also don't have fail, fail, and X. That is in between these two. We also don't have it. And the next one to follow. So with this one too, we have so many of them. We could think of A union B, but because event A and event B are finite, with this one we could just add them as we have in here. And A intersection B, what they do have in common, they do have S in common. And also they do have this FFS in common. So that is why we have A intersection B to be what? So, okay. So this is how we get to what? Come up with our properties, that is our union, our intersection. And as we move forward to, we are going to be dealing with others too as well. So let's look at another one which we call a null event. Now, you guys remember your null set, a set which has no elements in there. Now, remember that you represented your null set using this symbol that we have here, okay? Same thing is being applied once it comes to our probability. Now, a situation or event where we have no outcome, that could be mean that is what? A null event. Now, this null event is something that is used to represent a mutually exclusive. And remember, the mutually exclusive, that is when we have an event which do not have anything in common and as such cannot at the same time. These are mutually exclusive events, or other words, we could term it to be a disjoint set. So let's take a look at this example, which involves the automobile industry. Suppose there is a city in Ghana which has 3 automobile dealerships. For instance, let's use Accra, either Accra or Kumasi, where we have these automobile dealerships. So let's take Accra. So let's say in Accra we have several dealerships. In this case, we are looking at 3 dealerships. So in the first case, we have the GM Motors, who deal mainly in what? Selling of what? Chevrolet and that of what? Honda cars. We also have the Ford dealership, who deals mainly in Ford and Lincolns. And finally, we have the Toyota dealership. So these are the 3 dealerships that we would like to study. And suppose that we like to perform an experiment that consists of observing the brand of the next car which is going to be sold. So in this case, we could represent that is A, event A, referring to what? That of what? The GM Motors, cars being sold by the GM Motors, that is the Chevrolet, and that of what? The Honda. We could also take a look at that is event B, which is mainly the Ford dealership, who sells mainly the Ford and that of what? The Lincoln. We will also finally look at what? The Toyota. So if we are to look at these 3 events and we are looking at an experiment such that we want to determine the next brand of cars, you could see that these 3 dealerships, although they do sell cars, but once we talk about mutually exclusive, that term is being experienced here, in the sense that these 3 dealerships all are at different places. And if as a buyer, we would like to see the kind of car that you shall buy, because we don't have all these 3 dealerships at a place where a buyer or a customer could select any of these cars all at a spot, the mutually exclusive term comes in here. So if that happens, it means that we cannot really ascertain the kind of car the person is going to buy, considering all these 3 dealerships. So in this case, such an incident, we term this to be a mutually exclusive, because the next car sold cannot be both at GM Motors and the same as what? Ford. So unless this is going to be possible, unless perhaps all these 3 dealerships come together, or they should merge that company so that we can have all these cars all at a particular position. for a customer to make his or her choice. Now, let's take a look at when we have more than two events, okay? Because from the previous sessions, we've had A intersection B, A union B, and all that. But let's try to see if we should have more than what? Two events. Now, just as we did do those operations such as the union and intersection of two events, this can be extended to more than two events. So for instance, suppose that we should have event A, B, C, D, and we like to determine their union. That will be the same as A union B, union what? C. And that could also be done. Now in that same case, we could also have mutually exclusive events. And remember, mutually exclusive event implies that these events have nothing in common and for that matter cannot at the same time. So we could also look at their intersections, that is A intersection B intersection C. Now all this is something that we are going to look at, but let's try to portray everything we have here on the Venn diagram so that we get to see what is happening. Now remember, in the case of two events, we could have a Venn diagram of event A and event B. Now this shaded region here refers to their intersection, that is intersection of A and what? B. And here too we can have what? A union B, referring to what? The combination of what? A and that of what? B. That is more or less like what? Their sum. Now in this case where we have the shaded region happens to be the A complement. Remember, we have event A here, and outside the event is the complement. We could also have mutually exclusive events where they have nothing in common. And looking at the three events, we could have A, B, and C. So this where we have the shaded region refers to the sum of event A, B, and C. That is A union B, union what? C. And finally, we have their intersection, that is A, B, C, and that is what we have in this small region that we have here. So this is their intersection. So this brings us to the end of this session, and I'll see you at the next session.